Does anyone go back and watch the live stream?
I've had a very, yes, I'm very intrigued. Yeah. We're ahead of all our other classes. Alright, we'll check. No. Yeah.
That's what messed me up.
I did not know she did that draw, y'all. I figured she did. Drivers on the left.
Are you trying to stereotype?
That explains why people compare everything else to everything else to not that any of us yes, you did. But it's
This would be fun.
you hit like a dirty. God, you know what? It's like a gorilla. Yeah, that gorilla came very
Well, dog.
because I hold that up.
Oh.
Obviously, you're a little dog.
I can't even remember anymore. She got me so sidetracked. I keep thinking like a real hit me in the face. Right. You slapped me in the face one time. I do. I was surprised looking at me. Because everybody looked at the trash room at me. I was like, oh my god.
I don't remember that. That was the hardest one.
You didn't like
What's the main nature?
He says,
So bad. We would take your stuff.
Did you hear how we said it?
Did you ever have to do that across the classroom? And your whole pantry you fill it.
Anymore.
Yeah.
What about in John Brown class?
Yeah. All the boys.
Yeah, that's why y'all got slapped all the time.
Come on now. Turn me up. You've also wired.
Okay. Just say, okay,
You
now.
don't understand what
Living down.
it's so bad.
What do you mean? How was it bad?
I just don't understand.
What do you mean bad?
Don't understand.
Sorry, mommy. What happened?
No, you understand. You always did.
It's like, it's not surprising to me anymore. You're like this. Was that a bad influence on you?
I mean, you didn't really do anything.
I don't think you found that good clothing.
I had that bad influence on
No,
me.
not really.
Like when we first started, we knew we first started friendship.
Today Friday? Today is Friday.
Now I'm here today.
Take a minute, picture.
Let me take it.
I know you lying.
Well, I'm not all of them there.
Or you can throw it over.
It always seems like he's done.
Gosh, what life, dude.
Watch my.
Why did you get to this school?
You act like this around the
I only lived in the building for almost 3 years. In March of 3 years. Probably from hanging out with us.
I probably feel like a dope one.
Especially on that bus, we get wild.
She's on
That's around 6
Something was not doing on the bus the other day. Lightning and Jordan on the bus.
This is that turn to this, man.
It was literally Lightning and Jordan.
We did that.
We were sitting in front of us and talking.
I wish I got the run in front.
I think we had to do like that game.
And we
Hey,
sat
all right.
on
heard her.
Could be. Dude, I'm so happy. Is that the cat?
I just
You
wondered
know,
what
you
your
get,
mom
like, half the time y'all are getting all water stuff out, like, up the wall, so you know,
Yeah,
you
like, you just jump.
I mean, basically, it's me and one of them got along fine.
I'm talking about the same bed. It's a bed.
She was a good kid.
Yeah, right. Probably. I told her to text you. Doesn't talk to you on here.
Ain't no way. So what I'm talking about. Oh my gosh.
I literally told her my name and her phone used to be Trouble T. Cause she didn't agree with all the stuff I did. Now I can't come into Trouble T.
We start talking about it.
Me?
What it is.
Look at the dude now.
No, me and Morgan have had our own set of issues. This is the only, we got little issues. This is the.
I actually put them on.
Of course it is. I'm not being always. Well, you don't want it the same guy.
What was it? Dave?
I know.
I've been wanting to do that for like the past year now.
Yeah, just so you guys are like doing things.
Every single one you turn around like, hey, what you got?
I know she fell to the ground. She's hanging up the show. I can't believe this. I am.
Sorry for that delay. What I passed out to you already was obviously the initial analysis worksheet, so you can kind of get a look back at that. I passed out also this review, it's a review study guide. I like to call them the things that come before the exam, a review study guide, because then it just covers all the bases. Because oftentimes students are like, hey, Mr. Wright, do you do a review for the test? Yes. What about, do you have like a study guide? Yes. Because by being a review, it's a review of the information, but it also helps you practice some of, reusing the same skills and information. Because essentially your job is to pay attention, gather notes, collect information. I present it to you. I give you opportunities to practice with it. I'll allow worksheets and activities. And, some of the stuff we do in class. And then you use it and practice it in class. While you practice using your notes to help you answer questions. So much so that you don't need to use your notes anymore. So that you come to the exam day, you prepare so well that you no longer need to use your notes to answer questions, which is perfect because on exams you get no notes but yes questions. Are you there? It makes sense, doesn't it? It's like full circle. It's like, wow, you've really explained how education works. Sort of, but you know how this is too. I mean, I'm not telling you anything brand new, right? This is all like, what you come to understand for the most part. So, that is what's going on. Another news. What about the do now? You should have this out, graphing periodic trends out. We're going to look at that first. This is all the possible ways you think questions could be asked on the exam. That was literally that's like a review tactic. Hopefully you've been doing this do now. And I see some of you have figured out a pattern where you do the do now on one sheet of paper. That's excellent. That's perfect. That's exactly what you should do is just use one piece of paper and then just do the do now of each day and just put the date. That's it. Like a running list of do nows more or less. And look, it's solely to get you activated. And normally, like the way you get a score for it is like you do it now, or you don't do it. That's basically it. You do it right now, immediately, and I can tell, like there's no doubt that you started right now working on it, then you'll earn a 100 when I take a grade, which is sparingly, but I do walk around and notice it. Or I'll just look at you, and if you're obviously clearly talking to somebody else and not doing it, that would be a place where it's easy to say, oh, 0. right? But typically grades are like 0, 50, 100, every once in a while 75, 25 is in there too. So, hello? Hey, exams on Tuesday. Y'all, we've basically covered new content except for some of the trends activities, which we just need to make sure we go over the notes. So you got the trend, you got your graphing periodic trends out, and you've got the notes you took on the periodic table. Remember, these notes included and started with atomic radius, right? Atomic radius, ionic radius, ionization energy, electronegativity, etc. Hello? Are you there? Yesterday we ended class with the general trends of each of these four. And then I got up on the lab station and showed you, hey, electronegativity increases in this direction. And you should have copied this down in your notes. Perhaps the same notes that you wrote down these definitions. Hi, did you write down these definitions? Okay, they were on the slides that I posted on Monday and Tuesday of last week. Okay, and then what you should add to these notes is this image we talked through yesterday, though some of you may not have had a chance to do it. Just do a little sketch of the periodic table. Watch me. Watch me. Watch me. Done. Right. That's how fast it takes to sketch it. You don't have to cry about it. Like, dry them up. I got tissues though if you do. Also for any of your tiers, I have buckets. You can just weep directly into those buckets. They're just through this lab room right here, and they're in there.
Did you save them?
Huh?
Did you save them?
Yeah, I have these, but I have them stacked up, and if the students like, because all the, I consider complaining also tearful, even if you don't literally cry. But Mr. Knight, look, I got some buckets for your tears. Just put them right in there, just right there. It's a great collection reservoir for your tears. Yes.
You have a box like you just go like this?
No boxes. I do have some boxes, but not to live in. They're too small. I know you may be like, well, I can't find anyone moving in to a new house. I get it. And maybe if they're moving in, maybe they're just keeping the old refrigerator. I mean, then you're just.
Warehouse department.
There you go.
Mr. Knight,
Yes.
can I see the cable register in the front office for a few minutes?
Here she comes.
Thank you.
Yeah, so you're looking for that nice cozy box, and it might just be scarce. I mean, it could be on a ship outside of Long Beach, California. You know what I mean? Supply chain. Okay, you may not think about that. Okay. Anyway, what we're saying here is, and I want to use this, but I also want to get up on the lab station again because that was fun.
Did you do that for all your other classes too?
Just the only other class of chemistry, yeah. So check this out. This electronegativity. Here's what it means. Oh, let me do this randomly so we don't think I'm calling any of you out, and all of you get a chance. Please pause. I'm pulling up the random student generator for your class. Did y'all know this existed?
No.
Does any other teacher use popsicle sticks or something?
Mr. Brian?
Yeah.
Mr. John
So
Brian?
Google. The thing is it has a list of all of you, and it randomly chooses. So and it remembers where you left off the day before. So Jaden, in terms of electronegativity, which vanadium, iron, which one has a larger electronegativity?
Iron.
Iron does. Just based on the trend, which one has a larger electronegativity? Iron over vanadium. Why? Because it's further to the right. So you here looking at home, I don't even know if you can get this right here, but you have vanadium. This is going to show vanadium and iron. Iron is further to the right. So that's how that's going to work. I don't know that this is actually going to be useful. We'll see. That's too low. Hey. Anyway, you get it. I'm just going to go straight up right there. Okay, now we'll keep it normal. You're just going to have to listen to me at home. All right, and you can look at your periodic table, people at home, and then pause it. You can pause it at home. If you're watching the video, pause it, and then look for the stuff yourself before the student answers it. Thank you, Jaden. You're right. The iron is further to the right. And look which way electronegativity increases to the right. All right, so now what I want you to do, Jaden, I want you to model how everyone else should answer. Okay? What were you going to say?
So which one would have a higher electronegativity? Would it be nickel or silver?
Nickel or
Silver.
silver? Okay, so you have to have more information to be able to answer those specific types of questions. You would need to know, there's no like precedence. It's not like, okay, further up is more important than further to the right. It depends on the comparison. So you need more data to say, okay, nickel, silver, those are diagonal from each other. One's further right, but one's further up. How do you know? I won't ask you those types of questions because I just want you to realize that there are general trends. And here's the deal. This rule is this line represents a trend. Everyone say a trend. Trend means it's significant and notable, right? Does it mean every and always? Y'all know what's trendy in fashion, right? What's trendy in fashion for boys nowadays? Does every boy dress that way? No. So this is the case. In reality, the true measure of electronegativity for cobalt may not be more than iron. Are you with me? But we want to say based on the trend, cobalt's more than iron. Iron's more than vanadium. Are you there? Okay. And I won't, like I said, I won't ask you things that aren't obvious. It'll be an above or to the right or both. Like this. And Jaden, here's how you answer this question. You'll say iron has more because it's further to the right. Because literally it's just further to the right. Are you there? Okay, let's try another one. Aaron, let's look at phosphorus and copper.
Phosphorus, because it's higher and more to the right.
It's higher and more to the right. Are you there? Electronegativity increases that way and this way. Let's do one more just to really perfect it. Bryson. Good, you were just about to ask anyway. All right, how about this? Scandium and cesium.
Scandium.
Because?
Because it's further to the right and more up.
And more up. It's more up and to the right, and electronegativity increases in that way.
Right.
Just to get... So in this case, we say that F is the highest, fluorine, and FR is the lowest. Why is FR the lowest? It's the furthest down, which is opposite the arrow, and to the left, opposite the arrow. Are you with me? However, fluorine's the highest over here. Why isn't helium? Or why isn't neon? So another thing, a skill you have to understand is the periodic table is organized for various reasons. We'll look at that. You've probably seen it in the notes, but I'm going to go over that as our flyby. But helium behaves when it interacts like a group 18 element. However, it often behaves and acts like a group 2 also. You see how this looks like it's missing a square or a rectangle? That's because helium can act like this and like that. Are you with me? When it behaves, it acts like, with other elements, it acts like a group 18. When it's acting by itself, it sort of acts like a group 2 or like a hydrogen, a little bit larger hydrogen. Are you there? Okay. So, because of that, neon and helium, why don't they have higher electronegativities than fluorine? Because of the definition of electronegativity. Electronegativity is, ooh, I want another electron. I just really want to be extra negative. Are you there? How bad they want an electron. What do you know about group 18? They're noble gases. They're stable. Another word for that is inert. Everyone say inert.
Inert.
What does it mean to be stable and inert? They have 8 valence electrons, or here's a better word, complete outer shell. Helium only has 2 electrons, but it only has 1 outer shell. That's okay. That 1 outer shell only holds 2 electrons anyway. Are you there? Cool. So it only holds 2 electrons. It has a complete outer shell. That's what it does. By having a full electron shell, everyone say full electron shell.
Full electron shell.
It's stable. It's full. If it's full, it doesn't have a hunger anymore. Are you there? Imagine these electron shells are like the Cookie Monster and the electrons are like cookies. Okay? They can not change their identity and eat more and more and more. Are you there? But once they reach full, they're good. All of these are full, and if full, they don't want any more. Are you there? So they by default have a 0 electronegativity. They're content. Not really 0. It's close to 0. Some of them are really 0. Some of them are close to 0. Because there's obviously these are trends, and it's not exactly precise every time. Hello? Are you with me right now? So for this rule, electronegativity, we say fluorine has the highest because it's so little, and it has only one more. It just needs one more to get to 8, and it's little. It's not like it has a bunch of other electrons. It only has 9 total electrons. If it just can get one more, it can have 8 on the outermost shell, and it can be so content. What's the magic number, though? 8. Everyone say 8. 8. Helium and hydrogen just want 2 because they got the lowest energy level. But every energy level higher, they want 8. Hello? Are you there? Okay, it just needs one more. Now look here. Chlorine just needs one more, but it's bigger. It has another layer of electrons. And so it's like, okay, I really want one, but I don't want one as bad as fluorine because I got others. Are you with me? I got 8 others. Chlorine's like, look, I've got the 8 that fluorine wants, plus 7 more. Are you there? Because chlorine has 17 electrons. You catch what I'm saying right now? So fluorine wants it the most. All right. Ionization energy trends in the same direction. Can you figure this one out? Let's see. This is crazy. Dawson. Zinc versus ruthenium. I think you're right, too. Why? Further up and to the right from ruthenium. Zinc versus ruthenium. Zn versus Ru for those at home. Notice, further up and to the right, zinc, further up to the right, so has higher ionization energy. Let's do one more little practice like that. I feel like, hold on. Someone's at my door. I just want to make sure it wasn't a danger. It's not. We're good. I do want to make sure something else isn't going on too. Okay, good. All right, next person, Emily. All right, oxygen and phosphorus.
Oxygen.
Has a
Higher ionization energy.
Because why?
Is further up and to the right.
Further up and to the right. Are you there? Does this make sense how to do this? Now on the test, I'll give you an example of what, or I'll show you an example of how we'll do it on the test. But it's essentially just like this. You have to memorize these 2 trend up and to the right. And then this one trends down and to the left. Now, based on the definition of ionization energy, the highest one in this case is helium. Because ionization energy is sort of the opposite definition of electronegativity. Electronegativity is wanting bad another electron. I just have a lot of anxiety towards wanting another electron. I just want it right now, and I want it right now. Like a kid at any toy store, right, or the toy section at Walmart. Ionization energy is someone who's greedy, is a greedy toyer, greedy electron holder. Ionization energy is like, no, I'm good. Don't touch my electrons. I'm good. So they hold on tighter. Are you with me? Ionization energy is, I'm holding on with a lot of energy to things that I already have and don't come near me. I have a very sophisticated security system. We're going to AI you, and then you're going to get a drone strike to your face. Lots of energy expended at the expense of protecting the electrons. Whereas electronegativity, remember, is, ooh, I just want one more. Let me just get one more. Ionization energy is like, don't touch me. Don't touch me. Don't touch me, bruh. As you're wont to say. Or breh, if you really want to go with the EH inside there. I spell it B-R-U-H and then B-R-E-H. Not that I text it, other than in jest. Don't worry. I get it. It's lame. I'm old. So, just don't. Right? That's what you really want to say. Just don't. Right? Cringy? Is that what you'd say? Anyway, let's keep going. Atomic radius is the opposite effect. Atomic radius basically means size. We'll say atomic radius equals size.
Atomic radius equals size.
So it's really a substitute for size, so it's not exact. But I can ask it this way. Tantalum, radium. Elena, tantalum, radium. TA versus RA. Which one has a larger atomic radius?
You said largest?
Larger atomic radius.
Would be RA,
RA, because why?
that is more down.
More down to the left. Are you there? Now another way I could say this is, which one of these has a bigger atom? Bigger, you hear what I'm saying? Bigger versus larger atomic radius. More atomic radius, bigger atom. This is a substitute for the word size. Are you there? Let me do one more. Michaela, perfect. All right. Nitrogen and nickel. Which one? Because why? More down to the left, and that's which way atomic radius trends. Hello? Okay. So how does this work? Essentially, what? We got them again? Okay. Essentially how this works is, on the test, what I'll do is I'll give you, and it's a little bit more explanatory. Obviously, I want to up the level a little bit. But I want you to have a preview of it. Listen, are you following me? Here's how you can prepare for the test. When I go over what's on the test, prepare. Use that to help you prepare your focus for the test. Okay? So what I'll do is I'll pick an element on the periodic table. Let's just pick one right here, sulfur. And I'll say, look at sulfur and its neighbors. It's the neighbors that share an edge with it. What neighbors share an edge with sulfur? He's not here. Kyla?
Oxygen,
Oxygen.
chlorine,
Chlorine.
fluorine.
Not fluorine, that's a corner. So this is a good thing. The distinction is shares an edge. Specifically shares an edge. So oxygen, chlorine,
P, SU.
phosphorus, and selenium. Good. Are you there? They share a edge of its box, of its tile. Are you there? Does this make sense how I'm asking the question? It shouldn't be a shock when you see on the test, look at the neighbors of a certain element, like phosphorus. Okay, look at what it shares an edge with. Okay, now compare sulfur to its edge partners on all three of these terms. Are you there? Sulfur, let's try it. Let's see if someone can give it a go. Bryson, you're up again. How does sulfur compare to, just choose any edge partner?
BR?
No, direct an edge to it. Let's direct, like touching an edge.
So like touching any one of the sides?
The sides, the edge, yeah.
Okay.
Not corner.
Chlorine?
Chlorine, okay? How does sulfur compare to chlorine on any of these factors?
It has lower electronegativity.
Yes?
You mean to say something problem?
Yeah.
It has a higher atomic radius and a lower ionization energy.
That's perfect. And that's with a one edge partner. Could you do that with each of the other four? Or each of the other three here? Selenium, phosphorus, oxygen?
I thought you meant like the actual like corner.
No, yeah, no edge. Just the edge.
Okay, yeah, I got you now.
Yeah. Yeah, and that's why I'm doing this exercise, is to clarify what I mean by side, edge, tile, things like that. This is a tile that represents sulfur, and it shares an edge with chlorine, oxygen, phosphorus, selenium. Are you there? The best way to learn some of this stuff is just to try it out on your own with what I'm telling you, your interpretation of it, and then correcting it from there. Are you there? This is a lot of the times the method in chemistry, because that's how things were discovered in chemistry. People had a thought, they tested it out, it was wrong or it was right, it was right-ish, they fine-tuned it, or if it's wrong, they scrapped it and changed directions, and they figured stuff out. And now we have textbooks full of that mess. Hello? They just accumulated it. All right, so sulfur. He said, just to reiterate, it has less electronegativity, less ionization energy, and more atomic radius than chlorine. Okay? Another way to say it is it's less electronegative, has lower ionization energy, and is larger than chlorine. has larger atoms. Hello? Do you see this right now? Is this easy? Now watch this. I'm going to ask you on the test to do all 4. So you just have to repeat that sentence. Or can you think of a faster way to compare to all of them in like 2 sentences? Macy, let's give it a shot. How could you compare sulfur to all of its edge partners?
I'm gonna need some help.
That's fine. I'm totally guided by that.
So just pick anyone.
Pick any of them to start with.
Oxygen.
How about let's start out this way. Say sulfur
Sulfur
has a larger
has a larger
atomic radius.
atomic radius.
Which one does it have a larger atomic radius than? Oxygen. And
Chlorine.
and the way you know that is because it's further below oxygen and to the left of chlorine, right? And that's the way atomic radius says. So sulfur has a larger atomic radius than oxygen and chlorine, but smaller than
Phosphorus and SE.
selenium, Se. Yep. That's one sentence. Phosphorus or sulfur has a larger ionization energy and electronegativity than phosphorus and selenium, because it's further up and to the right of those. And a lower ionization electronegativity, and lower than oxygen and chlorine. 2 sentences. Do you see how that works? I want that to sink in so you can prepare yourself. Okay, good job, Mason. That was a really hard bit to go with, but you stuck with it, so good job. All right, how do we feel?
Okay.
Atomic radius goes this way. Cool. All right, and let's think about this. Let's just make sense of this. Okay? We made sense already about ionization energy and electronegativity. Ionization energy, we're going to go back through the definitions. We're going to read them together, even though you've already taken notes on them, Evan. But we've talked about them in some regard. I want you to understand, though, how these work, why these work the way they work. Right? This is chemistry, and I'm not going to tell you any lies. Here's why it makes sense the way they do. Oops. No, that's fine. It only does a little bit. All right. So check this out. We said that fluorine is smaller. It doesn't have many electrons, and it only needs 1 more to get to 8. Right? That's why it really wants 8. That desire for the 8th one is called electronegativity. Everyone say electronegativity.
Electronegativity.
Okay. It desires that last one. Are you there? Say, I'm here.
I'm here.
I'm here.
I'm here.
Say, I'm here.
I'm here.
Okay, good. Yeah, that was the emphasis. You had to say here. You know, here. I'm right here. Okay. Whereas, and it's few electrons, and it really just wants that 8th one. Are you there? That's why that makes sense. Helium. It's content. It's got a full outer shell. Done. That's it. It's the most full. If it loses 1, it's only 1 more away from being full. If it gains 1 more, it'll only be 1 more above being full. It's so good and content because it's 1 away and it only needs 2, so it'd be halfway in 1 instant above. Are you there right now? Like, it's so good energetically, so it holds on so tightly to that last one. Hello? Okay. Therefore, it has a high ionization energy. Those sort of make sense because we can tell based on the number of electrons they have in their outermost shell. Hello? Okay, cool. Atomic radius also makes sense. Why does it make sense that every element going down a column here gets larger in atomic radius? Why does that make sense? Tell me about it.
Electron shells.
What do you mean electron shells?
They gain more shells, so
How do you know they gain more shells?
the period.
The periods. As you go down a group, what happens to the period number? It increases. And what does the period number tell us?
The number of electron shells.
Everybody say it. The number of electron shells used. That's what we copied down to memorize. Are you still following? Hi. Everyone wave at me. Even Evan. Yeah, well, he's doing it from like that. All right. It makes sense. Okay. That's how it gets bigger that way. Now, how is it confusing, though? Why doesn't atomic radius get larger going this way?
Isn't it something about like the force?
It definitely does have to do with the force.
No,
Okay, so that's actually going to be how we make sense of why it gets bigger this way. We're going to make sense of why it gets bigger going this way along the periodic table, like in range. Oops, excuse me, in range with the atomic radius. But why would it make sense to say, I think atomic radius should get bigger going this way? Why doesn't it get bigger going this way? Like, why would it make sense to say that? More electrons added, right? Think of it this way. If cesium and its electron shells is a box, it has one in the outer part of that box. You stuffed in one layer of stuffing. Yes? One more packing peanut. Barium stuffs in another one more peanut. How does that not occupy more space? Are you with me? How does adding more stuff not make it larger? You would think, okay, barium has one more, it should be larger. Lanthanum has one, let's use row 5. Rubidium has one in the outer shell. Strontium has one more, it should be larger. Yttrium has one more, it should be larger. Zirconium has one more electron in the outer shell, it should be has one more extra electron, it should be larger. But it's not larger. Look, I can't say this enough. It's not. It increases in this direction. It seems like it should go this way, but it doesn't. Do you understand what I'm trying to say here? Do you understand why it should increase going the right side? You're adding more stuff. Yes? Yes? Okay. But how about why? Why does it not get bigger? Why doesn't it get bigger like that? Why is that wrong? Because when it adds an electron each time it goes, what else does it add? A proton. What do we know about protons and electrons? Yep, Aaron just did it right there. They're oppositely charged, right? So they attract. So it turns out there's this other phenomenon that was discovered, that was noticed. As a new electron is added, so is a proton, or vice versa. If a proton's added, so is the desire for an electron, therefore another electron is added. And when you add one of each, the center, which has protons, and the outside, which has electrons, which are oppositely charged, you're making the center more positive and the outside more negative. Hello? So that entire layer is more negative and the entire center is more positive. And what happens when you have a positive and a negative sides of things? They attract more. So it actually, the center nucleus pulls in to the space. Are you there right now? Are you picking up on this? So you think here, all right, rubidium, one outer electron, the outermost shell. That outer shell is far out from the fourth one. The fourth shell is like here. The fifth shell is like this. Let me give you some perspective. Shell 1 is like a ping pong ball. Shell 2 is like a golf ball. Shell 3 is like a racquetball. Shell 4 is like a tennis ball. Shell 5 is like a softball. Shell 6 is like a volleyball. And shell 7, is like a basketball. Are you there? We could use other ball shapes to really illustrate this. But the difference between a basketball, full-size NBA basketball, and a volleyball is pretty clear. Are you there? So to change that size is to make it larger. That's why adding an extra shell does make it matter. But check this out. Rubidium has one outer electron. Hold on, let me make sure this is an emergency. Okay, it's not. Strontium adds one more proton and electron. So by adding one more and one more, it shrinks in just a bit. So if 5 is out here, it becomes a little bit squished. And then yttrium goes like this. And then zirconium. And then niobium. And then molybdenum. Technetium. Are you with me? And it slow squeezes, but just by the most minute little squeeze. Are you there? So, by adding more protons and electrons, it gets smaller going that way. Does this make sense? That's why atomic radius makes sense. Hello? Are you there right now? This is all good stuff.
It's amazing.
It is kind of amazing, actually, yeah. All right, so we've just made sense of those three ones right there. We've got one more to make sense of. Atomic radius is basically size. The way it's done, and you have this definition, atoms are not really like balls. They could fit inside of shapes of balls, but ultimately they take on a different shape. Their edges are fuzzier because electrons are constantly moving. They occupy space. They move in a shape and occupy space. They don't actually create edges. Are you there? Electrons are all over the place at one time. The way they measure is they take two identical atoms and measure from distance from center to center, nucleus to nucleus. What do you call the center of an atom? Nucleus. Everybody, what do you call the center? Nucleus. Okay. Do you know what's home to in the nucleus? Protons and neutrons. Neutrons basically add bulk and stability, but they end up actually over-stabilizing it, and it becomes unstable. This is why balance works. And then what floats around the nucleus? Electrons. All right, just some other reminders. What do you call I should do it on the board here, sorry y'all. What do you call so you got protons plus neutrons, 0. Electrons have a minus sign. Are you there? Okay. What do you call an atom that has an extra neutron or a different number of neutrons than the average amount? Isotope. Extra neutrons is called an isotope. Whenever they do extras, I don't think they meant to do this, but they use I letters for whatever reason. When there's extra neutrons, it's an isotope. Right? If it has the number of protons, that's its identity. Hello? Whenever there's another extra a neutron, it makes it an isotope. The identity is the same with the new isotope. Hello? Like different apparel, basically. What do you call something that has an extra or fewer or a different number of electrons? An ion. Hello? This is awesome. More extra neutrons, you call it an isotope. Extra electrons, you call it, or extra or fewer electrons than normal, it's an ion. What happens when you change the different number of protons? It gets a new, ready? Identity. See what I did there? Eyes all around. Eyes on me, eyes all around, eyes. Are you getting this right now? Are you seeing it? Fresh, you're probably seeing it with fresh eyes. Did you get taught in physical science about electrons, protons, and neutrons?
Yes.
Did you ever was it made the connection for you about identity, isotope, ion?
No.
So, good. Ionic radius is the distance between the nuclei of a bonded cation. Remember, cation means positive ion. Ready? Watch my terrible handwriting actually help us this time. Cation. Cation. What does my T look like? A plus sign. Not a cation. Not a cation. That's like a strange abbrev for a trip with my family to the beach. Not a cation. Not a vacation. Not a vacation. Not a vacation. I don't know how you say it, but it's not that. Okay. Cation. And then a negative ion is an anion. It's just an anion. An anion is an ion that is negative.
I remember it's a negative ion.
An ion, a negative ion. That's actually really good. Negative. I mean, not that I'm shocked, but it'd be really good. But it's, I haven't heard anyone say that before. A negative ion. Hello? If you just wrote down the words a negative, oh, an ion. It's an an ion. An anion. Everyone say an anion is a negative ion.
Is a negative ion.
Whoa. I know. A negative ion. Word search. Got it. Okay. You gotta know those things. Now look here. A negative ion. An ion means it has an extra what? Ion equals what? Different numbers of electrons. One extra or one fewer. Hello? What charge do electrons have? Negative. If you gain an electron, this is easy. If you gain an electron, what new charge will you have? Negative. You gained a negative thing. Hello? You get. Let's use the word get. Get an electron is to be more negative. Hello? And we'll say get an electron, be negative. Okay. Drop an electron, and we'll say drop an electron, be positive. Are you with me? Are you following me? Okay. Now, ionic radius. The way it trends is not with atomic radius, not with the normal size situation, but it still makes sense. Typically, the way we understand radii of ions is we don't really want to compare like one element to another across the periodic table. We'll compare one element to itself or something very similar. So like this. Let's compare sodium. You know sodium, the easiest of all the elements? Sodium, because it's sodium easy. Sodium, when it forms an ion, what oxidation number does it have?
1 plus.
What oxidation number would you write on your periodic table above sodium's group? 1 plus. That's its oxidation number. What's its charge? Its charge would be +1, right?
Wait. 1 plus is the oxidation number?
Yep, oxidation number.
Okay.
Hello? Hey, in math, whenever you write 1x, do you ever write 1x?
No, I just read it.
What do you do? The 1 is understood, right? We do the same thing here. So the same thing here is to say plus. Hello? All right, so sodium, the easiest of them all, is in group 1, and you write 1 plus above it, so it forms the ion. What that means is it forms ions that have a 1 plus oxidation number. Or like this, Na plus. You follow that one? Maybe I'm going red instead. Its ion is going to look like this, Na plus. You know what? Let's go to a whole sheet here. Let's go oxidation number, charge, let's say is +1, no, excuse me, 1 plus, +1. The ion it forms is sodium, easiest. So it looks like this, sodium plus. Are you there? That's the ion it forms. So when you wrote those numbers above the groups, you're saying everything in that group forms an ion and will look like this. So that potassium looks like that. Superscript. Rubidium looks like this. Are you with me right now? Does this make sense? What does it mean to be +1 on the charge, or 1 plus oxidation number? What does that mean? How does an atom, hold on, it's an ion, right? What did we say ions are? Different numbers of electrons. Hello? If it's positive, what has it done with electrons? Lost the negative thing. It's dropped it. Hello? It dropped it. So it's lost an electron. Hello? Watch me here. Okay? If it loses a negative thing, it doesn't have anything to do with the protons. What will happen to its size? It gets smaller. It literally loses something and it gets smaller, like you'd imagine it, just like you would imagine in the other way. Because look, there's no proton involved. When you added a neutron or electron and a proton, the whole thing shrunk down. Are you there? Because they attracted more. So when you just lose just an electron, it'll get smaller. Let's look at the other way. Actually, I think it makes a little bit more sense to see this from. Earlier, when we talked about going across the periodic table, we said as you add an electron, there was also a proton, so it got smaller. What happens if you add just an electron and not another proton? It does what you think it does. It gets bigger. Hello? Okay. So here's how we would normally compare things. Is we'd say something like, all right, let's compare, let's go straight here. Let's go with all of them. Na plus, the ion it forms. Magnesium 2 plus. Aluminum 3 plus. And then let's go with phosphorus and phosphorus ion, and sulfur ion, and chlorine ion. I've just listed each atom in row 3 and its ionic form. Are you still with me right now? Have you understood? You understand what I'm doing right now? You understand what I just did? Why won't my clock just stop? Okay, there we go. What has happened to make chlorine be 1 minus? To go from here to here. It has 1 extra electron. Are you there? Okay. What about sulfur to become its ionic form? 2 extra electrons. What about phosphorus? 3 extra electrons. What about sodium then? 1 dropped electron. 2 dropped electron. What about aluminum? 3 dropped electrons. Are you there? You get what I've done here? Okay, here's how a question would be asked about ionic radius. Which of these is the largest size? Okay? But more importantly, it'd be like this. Between chlorine and chlorine minus, which one's larger? Why chlorine minus? Because it has an extra electron, so more stuff, but not a proton to squeeze it in. Are you there? So now it's just back to normal. This has more stuff, larger. Which one's larger here? Because it has more stuff. Let me actually go back and do this again. Watch this. Cl minus S2 minus. All right, P3 minus. Which one's larger? P3 minus. Now, of those 3 ions, which ion is the largest? Because it's the most negative, has the most extra electrons. Hello? Does this make sense? Do you see this? It has the most electrons and it is therefore larger. I want to circle them to make them larger as well. So we have a rule. The more why is phosphorus a larger ion? More negative things. Yes? So what's our rule then? The more negative equals what? Larger ion. Or larger in general, larger just in size. Larger ion. Hello? Alright, so let's try to figure this out. What's the order of size for aluminum, magnesium, and sodium? Which one's the largest, which one's the smallest of those three? Aluminum, magnesium, and sodium. Those ions.
Sodium was the one.
Why?
Because it lost 3 electrons. Or it lost, like, it lost the least amount.
Okay, so that way it's what? It's more negative. You know what's the opposite sentence that means more negative? Of more negative? Less positive. Hello? To say less positive means more negative, yes? Which one of these three, 1, 2, 3, is less positive? Sodium. See, it says plus. See, aluminum says 3 plus. Let's look at the sides here. Okay. So I didn't have enough room to really make sodium plus bigger, but sodium plus would be bigger than magnesium and bigger than aluminum. The more negative, the larger. Yeah. So let's put this into perspective now. Sodium plus, Cl minus. Does that make sense as a picture? Which one's the largest in my picture? Chlorine minus. Because it, and you can know why. Because it's the more negative. Sodium, this one is neutral. Neutral is less positive than Na plus, thereby being more negative. Hello? Y'all, this is stuff. This is man. I know it's some nitty gritty today. It was some nitty gritty. But we're gonna be all right. We're gonna be all right. All right, everyone want to go ahead and stand right now. We just covered some stuff. We're going to fly by some things that you've covered in your notes. But go ahead and stand real quick. I can lead you in what I like to call micro stretching. You can stretch as far-reaching beyond this if you'd like, but just for embarrassment's sake, I don't know why anyone would, but just in case, if you just go like this, the way we stretch is using our hands and our toes. So you're going to go like this. And you're going to reach and stretch your fingers as high as you can, but not move your elbows or shoulders. And go up on your toes, and then go back down. And then go down low. Slight bend of the knee, and then fingertips down. That's a deep one. All right, then ready? Then go back up on your, straighten your legs out, get up on your toes, and your fingers up top. Micro stretching. Man. When will the positive be bigger?
Which one is big, the negative or the positive?
The negative is the biggest.
So if it has, okay.
More negative the larger.
Okay.
Now here, this. If we compare, say, chlorine minus to cesium plus, which one's larger? So when we look at cesium, it is so much larger of an atomic radius. So my atomic radius is so big, its ionic radius is still big. This ionic radius is big, but still not that big. And it's not big because it's atomic radius. Its atomic radius is very small. Hello? So but I won't ask you those types of questions. You still need more data than that. But look here, just pointed out a question. Are negatives always larger? No. Look at cesium. It's so far down, it has a huge atomic radius. So its ionic radius, when it's a positive, is smaller, but smaller than huge is still big. Whereas chlorine has a very tiny atomic radius. So it has a much larger ionic radius, but much larger than tiny is still not that big. Can you see by my picture illustration here? This IR is still bigger than this IR. Hello? So is it a hard and fast rule? Every positive will always be larger than every negative? Not necessarily. But I think it looks better when you see these things graphed. Once again, ionization energy is when electrons, is energy required to remove an electron. It's a greedy electron holder. So looking at these two. Bohr models. Which one is a greedy electron holder? Holderer. Chlorine, because why? It just needs one more to get to 8. Sodium's like, look, if I lose one, I get 8 on the outside. So chlorine's it. Chlorine is a greater ionization energy. Electronegativity, the tendency to attract extra electrons. So we just said chlorine holds on stronger. What about chlorine's want for another? Has a higher wanter. If sodium doesn't mind getting rid of, has a low energy to get rid of, then it doesn't really want another. Are you there? Whereas chlorine really is holding on tight because it's holding on hope for that last one, so it wants that extra really bad. Electronegativity. 2, it's the other side of the same coin. Hello? Want to hold on so tight because I'm so close to 8 means I also want the 8th. Are you there? Okay, cool. Cool. So on your project, graphing periodic trends, here's the sample graph. We looked at these trends. You can see these trends appear when you graph the data. That's why it's so good to do. Watch this, though. We'll practice those later. Here is how atomic radius would look. If you watch my video, I feel like it was pretty darn good. All right? Like, it was pretty good. I feel like I really worked hard on it, and it was really specific, which is why it took 20 minutes to even elapse. Technically, though, it took me longer, to get an hour and a half to get everything together and edit and whatnot. On a Friday night, before I left for the natty.
What time?
Actually, was that Saturday? That was Saturday night before I left for the natty. After that, at midnight, I went to go pack my bag up to go leave for the natty. So next morning, woke up, made breakfast for the kids, got them off to church around 9:50, and then I left for the natty. 9 a.m. Got there around 9 p.m., so that was fun. No, it was 10 a.m. when I left, and I got there around 9 p.m. Only to find that my hotel room was overbooked.
What?
The hotel said I was 30 rooms overbooked.
You didn't even tell us.
I know I haven't told you this part yet. Got there at 9 p.m. in Indianapolis, basically a foreign country. Not really. It was just a foreign state. Not really foreign, domestic, but it's a different state. And we're like, okay, cool, we're here at the Quality Inn. We checked in. Here's our reservation. Sidebar, never use getaroom.com. No. Hotels.com, maybe, and even still scant on that one. Why did my computer just go to sleep? You should have done that last thing.
It's time.
It's tired. Still shouldn't have done it. Did it go off? I just forgot. Okay, still good. Woo! That was close. It was a close one. So we get there, we get on the phone with them, and we get to the thing, like, yeah, we're 30 rooms overbooked. We tried to call them a week ago. Like, well, you didn't call us. All you do is call us. We would have booked another place. We get it. Like, just let us know. Not 9 p.m. when it was 16 degrees wind chill outside. Yeah, it was cold. So we were both trying to call and get on the phone and figure that out. They tried to book us in another place, and it was a little sketchy. Like, it just was, the street lights weren't working very well, and they were blinking as we were driving. It just felt like, I didn't feel safe. And it was so late. I was like, the reason why I picked this other one was because it was like next to a Steak and Shake, and there were other restaurants and like 3 well-lit, gas stations. Which, by the way, it's just a good idea when you go to a new place, just to go to a place where you can recognize things that are like home. Right, like it looks like a busy. It looked like Arkwright Road in Macon. Just looked busy, like a hotel with a bunch of restaurants nearby. That's a good place to go because the hotel's got to be a certain level to not detract customers, they would never get any people to stay there. Anyway, so that's why we chose it, and we didn't choose this other Quality Inn on the other side of town, which had basically nothing. It just looked like a bunch of boarded up, closed businesses around. It's like, this doesn't seem as safe as where the first one I booked. So we called, we said, can we change this, please? And they said, okay, fine, and they did. And then they tried to book us in a Super 8.
Oh, no.
Which, don't get me wrong, look, I'm sure there are Super 8s that are fine. This one was not. I thought, I've never given a Super 8 a chance because I just don't know about Super 8. I've just never stayed in a Super 8 growing up. I always thought they probably aren't there. So we tried it. Well, you know what? The pictures look okay online. They were false. The pictures were false. Long story short, we ended up staying at the Super 8 anyway because it was 11:40 by the time we got to our new accommodations. That's what some have said. The lights were dim in the rooms even. It looked like they took furniture from other, like, OK hotels that threw out old furniture, and they just went to the trash cans of the other OK hotels and said, let me take that OK hotel trash furniture and use it as ours. I mean, it was all scratched and scuffed, and like the chair was busted in places, like with foam and stuff coming out all over the place, and it like had one caster wheel that was from obviously a different thing altogether. The one upside was they clearly redid the vanity sink, and the mattresses were new-ish. They were unstained, I should say. You might expect a place like that to have all kinds of brown and yellow stains on them. If you've ever seen a bad hotel, you know what I'm talking about. The downside was the sheets, which were very bright and clean, had cigarette burn holes in them. And they had signs all over the place saying no smoking or else you'll lose a $100 deposit. And I was like, some people did not worry about that sign. They just burn holes all over the sheets. Smoking in the bed? Come on, I mean, I get it. I get the chair looked kind of crappy too. You don't want to burn that. Probably that looked like it just needs to be burned in general, but yeesh. Anyway, I digress. So yeah, we ended up there. We ended up the next day canceling the next night and getting our money back eventually, and then we went and stayed at Drury Plaza. Shout out Drury Plaza. That place is awesome. Oh my goodness. It was like a 3-star hotel that tried its hardest to be like the Ritz, but charged like a 3-star hotel. So it was relatively inexpensive, but had awesome stuff. It looked awesome. So anyway, Drury Plaza. Drury. Anyway, everybody see here? You good? Now watch this. Some of your questions that follow up. They're just asking you to identify trends. Get this. The follow-up question, this is so cool. This right here, do you see it? Shows how trends work. This is like a cheat sheet. This can help you answer. Use this to help you answer some of those questions too. So the question is like, how does ionization energy trend across a period? Across a period. Ionization energy trends across a period. It increases across a period. Do you hear me? That's how you look at it. Use that as a cheat sheet to help you a little bit too. But more than that, look at this. What about atomic radius? Look at the period. You plotted it and you connected the dots of every group. Lithium, watch this. Lithium, beryllium, boron, carbon, nitrogen, oxygen. Those are all in the same period. You plotted those, yes? And that's the shape it would make? What about if you look down a group? Lithium, sodium, potassium, rubidium. Lithium, sodium, potassium, rubidium. That's going down a group. As I go down a group, what happens to the number? What is it? You say it, not me. As you go down a group, what happens? Which does that jive with the earlier image we have? Does that make sense? As you go down a group, what happens to the atomic radius? It goes up, right? That's how you make sense of some of these questions. Okay? Okay, how do you mean? Give me
Just reading when I read the question, it makes me confused.
Let me reword something like number 5. why are the properties of the elements graphed considered functions of atomic numbers? Why are they functions? Why do we have these trends that correlate with, that go with atomic numbers? Again, look. As you go down a group, what happens to the atomic radius? It goes up, right? As you go across a period, what happens to the atomic radius? It goes down. Are you seeing this right now? Notice what else happens. As you go across a period, what's happening to the blue number here? It increases. So we're saying, look, this way means more atomic number, but smaller radius. So we could say this. As the atomic number goes up this way, the size goes down. That's called a function. As one thing happens, another thing happens. Hello? You see what I'm saying? They go together. It's a function. Same thing here. As you go down a group, what happens to the blue number? It increases in chunks. So look, as you go down a group, the atomic number goes up as chunks, a chunk bigger, and the size goes up with the chunk bigger amounts. Are you there? Down a group, higher atomic number, larger radius. Are you there? Across a period, higher atomic number, smaller radius. When it goes one step at a time, one atomic number at a time, up, you get a shrinkage. Are you okay? Interesting is the periodic table is arranged by increasing atomic number. Right? You can go from left to right and read it like a typewriter or like words on a book. The blue number increases one at a time. Are you there? This makes sense. It's arranged as you read them in increasing order. But they didn't just put it in like a box. They didn't just say some here, 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 right? It's like this. Right? That's how you read it. It's arranged like that. So look, it's arranged by increasing atomic number, 1, 2, 3, 4, 5, 6, 7, 8, into groups and periods revealing other trends. What other trends? Atomic radius, ionic radius, ionization energy, electronegativity. Hello? Are you picking up what I'm putting down right now? Y'all, I'm like a cheerleader right now. I'm just breaking it down and cheering on the sidelines here. I just want you to make sense of these questions. Like, what do you notice is happening? Well, it looks like as the atomic number goes up, the trends do. Example. Give me an example. So how do they go? How are they functions? How about this? Why does it make sense? I want you to think in terms of, okay, atomic number is based on proton number. Proton number and electron number goes up, there's attractiveness. So the attractiveness causes it to shrink in size. So that makes sense of atomic radius. Do you see how we logicked that? Have we not been logicking those things along the way? Yes, that's what we've been doing. We've been practicing it. Talking about why it makes sense that atomic radius increases the way it does. Why it makes sense that ionic radius increases the way it does. And if it doesn't make sense to you right now, this has all been videoed and my voice is on there on display. Go rewatch this to study this component for answering these questions, which this project is due on Tuesday. The exam for this unit is on Tuesday also. Let's get to some other things. Notice these slides show some things. Watch the ionic radius come to life. Ready? Positives on one end, negatives on the other. We see the size of the negatives are all larger than the positives within the period. Look at this. Positive rubidium, though, is actually bigger than negative nitrogen. You see how this works? Because it's so big as atomic radius. Rubidium has a huge atomic radius and a relatively low ionic radius. Nitrogen has a small atomic radius, but a bigger ionic radius. This is bigger than this. Do you see that? I just want to over-explain this if I can. All right, I do have stuff for you to write down, for that matter, coming soon. First, let's go back to the history. We're going to fly through this really quick. I have some details that I want you to write down that I came up with. Here's what we need to know about the periodic table. And before you write down this stuff, we're going to write down the next stuff in a second. You need to know this is a general premise. And this may actually have to go over into the review stuff on Monday, where I go through the notes again, the notes that you've already taken. Why am I not spending more time on it? Because it is a review of physical science concepts. And it is no longer a chemistry concept. It is a concept you need to use in chemistry, but not to have learned in chemistry. Does that make sense? I need to understand that you've learned, to some extent, some of the stuff that you took notes on already. But, generally, you need to know enough of that stuff today for chemistry. How it was and how it is arranged. The chain of custody. Who handled it over the course of time? How is it organized and how does it lead to trends? Or how does the organization lead to trends or patterns? Trends just means patterns. And then we're going to do like a flyby of groups. You need to know generally a couple group names, like the most important ones. You've already said this. Yeah, group 18. What do you call group 18? Noble gases. Do you know what group 17 is called? It's technically called the halogens, but that's not as important. It's like the last one to remember. Here's your big name groups. You got noble gases, alkali metals, alkaline earth metals. Those are the big three metals, things to know. The next major group is this whole section. What do you call this whole section that's transition metals? Hello? That's the order of knowing. Noble gases, alkali metals, alkaline earth metals, transition metals. That's it. Those are your big group names. Why is this line so bold in that staggered staircase line? That separates metals from non-metals, yes? What do you call the right-siders? Non-metals, like gases, at room temperature. What do you call the left-siders? Metals. These are general trends, because some of these elements that touch the staircase are halvesies. They're half-breeds. They have some characteristics like metals, some like non-metals, and that's why they're so interesting. So if they touch the staircase, they're a candidate to be a metalloid. But not even all of those are metalloids. Let's see. Polonium is not really a metalloid. It's just really a metal. It actually acts like a rare earth metal. All right, trends themselves. And we graph the trends themselves. We've taken notes on the trends themselves. You already did number 5, and we just did number 4 right now. Number 4 we just did together by just announcing those names of groups. You need to know those at least group names. The trends we've already did. That was the whole we spent the entire beginning of class on. And then that little mini chart with the arrows on it. That's number 5. Number 4 we've kind of been talking about, like the reasons, like you add a proton and an electron, and that shrinks it down as you go across a period. But if you just add an electron, that makes it bigger, ionic radius. And it adds an electron because it wants it real bad, electronegativity. And it holds on to those close, so ionization energy. Pause a second. I'm going to post this slide, which answers those 5 questions. I'm going to post the questions and the slides that answer them into Google Classroom. So go look for that as well. You can back it up. I don't know whether they're going to dismiss this to groups or not, or whether they have club day or homeroom. So we'll see you in a second.
Everybody at Anderson said
Look at that review. Oh,
all the early
the classification of matter worksheet.
My homework? Oh.
Shucks, yeah, the homework one. Yeah, how about this? You turn those in to the tray, and I'll get them back to you on Monday, so that way you can study them still some more. But turn those classification of matter worksheets into the tray. If you're at home watching this, you can take a picture of it or send it to me. I posted it online as well. You'll find it on yesterday's post, I believe is what it's called. So put that into the tray. Thank you.
Did I do it right? Probably not.
Yes.
I think I did the whole thing wrong. Like, that's what it is. Huh?
Yeah, I think you go to, I don't really know what they're doing right now, they haven't announced anything, so you're going to have to text us. information on that.
Teachers and students, if you're not in these,
Thanks for watching. Tune in next time for another edition of Night Chemistry.